Talk of the session, and Nick Duffield is going to tell us more that we need to know about sampling.
Okay, thanks, Don. So actually, the methods I'm going to talk about could be used more broadly than in internet measurement, but a lot of the constraints and design considerations that went into it, come from the internet and the constraints of measuring there. So it's about size and it's about streaming. So here are two examples of large data sets from the internet. We've got network usage data, and a very current example is flow records. And flow records are summaries of traffic flows between origins and destinations with other common characteristics. I'll talk about that in a bit more detail in a minute. And the routers compile summaries of these, and they export them to ultimately to a collector where they can be queried, stored, correlated, and used for network management in general. They're quite voluminous, so just 1 gigabit per second of traffic can yield hundreds of these flow records per second. So you can end up with in a large ISP where you may be measuring flows on thousands of high-speed interfaces, you could end up with a terabyte or terabytes of these measurements per day. Another example is in network user data. So let's look at online social networks. So these may have hundreds of millions of users, and if you're interested in understanding the relationships between those users, those are the edges on the user graph, there may be tens or even hundreds of billions of these relationships. So if you're thinking from the point of view, not necessarily from somebody on the outside trying to measure, but somebody who's actually running an online social network who has this data available to them, doesn't have to crawl a graph or anything awkward like that, but really just wants to answer a question like, answer some aggregate question about what's some mean property of their users. They don't want to have to go scanning down hundreds of millions of users in their database to answer relatively simple questions. So this is why sampling can be useful. From the point of view of data volume, accommodating this measurement data requires storage and transmission, and eventually, as we want to run some queries on it, so there's processing. So for the example, in the flow records, we've got the bandwidth cost of transmitting the flow records from the router to some central collector for storage and processing. Query execution time, so this relates to the example I just mentioned. It's better to run queries over some representative sample than have to query your whole database of users. And there's also a question of, if we're considering sampling as opposed to other data reduction methods like aggregation or filtering, sampling at least gives you the flexibility of being able to run arbitrary queries in the future on your data. For example, if a new network attack signature is developed, you want to go back and apply this to past flow records to discover the origins and the onset of that attack when it started happening, even though you didn't know what that signature was at the time you did your sampling. So I don't know if people here are generally familiar with the idea of flow records, but since it's a motivating example, perhaps it's worth just covering it in a bit more detail. So here we represent on a timeline packets of different colors, and what the color indicates is a common property of the packets shared by subsets of packets called a key, which can be a combination of the source and destination IP address, TCP UDP ports, type of service fields, and the flow records. These are compiled and exported by the routers, and the flow record contains the key information, packets and byte counts for the total, all the packets observed in that flow, timing information on the first and last packet of the flow, and some router states associated that the packets encountered when they traversed the router. And this is used in many applications: network planning and engineering, finding traffic matrices, or network security, looking at anomalous patterns of traffic, trying to analyze and trace attacks. And this is realized in Cisco's operating system, a feature called NetFlow, and also standardized within the Internet Engineering Task Force. So this is something that's routinely done and collected by ISPs. And well, here's an infrastructure in which you might collect these. So we have here we have a router center, which might be one of these in a city, and we have a number of routers. Traffic is traversing these. They're compiling NetFlow records, which may, instead of being exported directly to some ultimate high-level collector, are collected in a low-level collector in the router center, and there they can be sampled or aggregated or processed in some other way before finally being exported to the high-level collector, which is collecting NetFlow records from a number of these router centers. And so, here, one of the reasons we're sampling is that this transmission resource, which may be all the way across the country from the router center to the high-level collector, is relatively expensive. So this is one reason on resource grounds we want to sample. So what makes a good sampling scheme? Well, there are two aspects, one of which is the computational properties. And one of the key things we need to satisfy is we need to be able to work on streaming data. So the routers are producing this stream of flow records, very high volume. We don't have much time to decide whether or not we're going to keep a given flow record. We certainly don't have time to go back to the start. At the end of the day, you go back to the start of the day's data comprehensively and have second thoughts about whether we should have discarded a given flow record. We have to work pretty much immediately and decide whether we're going to sample or discard flow records. Even within this, even within a streaming scheme, computational efficiency is key, because these flow records are being produced at a high rate, so we don't have much time to work with each one. On the statistical side, we want good statistical properties. Accuracy of estimation. What we're doing is we're using the flow records we have to estimate properties of the population from which the flow records were drawn. So nice properties are unbiased estimation. So for example, unbiased estimation of all the traffic that went from source A to destination B during a given hour of the day, total number of bytes. We want to control the number of samples. And this relates to our resource constraints. And we may want to constrain this loosely or tightly. We may have a precise constraint. A fixed number of flow records we want to sample. And but on the other hand, we simultaneously want to control the estimation variance. The fewer samples we have, typically the higher variance our estimates are going to be. So there's a trade-off there we have to manage. So let's think about this in relation to the state of the art. Well, there's a large existing statistical literature on sampling methods. And if you look at Tilly's recent book, there's a review of a very large number of these. However, in the broad statistical literature, there seems to be not so much focus on implementation issues. And in some sense, this is natural because unless you're dealing with massive data sets, unless you have streaming constraints, there's not necessarily a reason to focus on the implementation issues. And on the other hand, on the statistical side, we found that many of the proposed methods are suboptimal in terms of estimation accuracy. Some methods have one side but not the other covered. But as far as we can tell, under the constraints we're operating, there's no existing method which fulfills our statistical and our computational aims. We're in fact going to take an axiomatic approach and identify a small number of desirable statistical properties and find a variance optimal sampling and estimation strategy, and then establish efficient implementations which are compatible with these practical constraints about streaming and data size. So let's talk about these properties in a bit more detail. So the computational properties first. So streaming. So by streaming data sets, we have these flow records. We have this high volume of data, these flow records presented sequentially, and we need to sample these, whatever we need, on one pass through the data with limited buffering. We may be able to provisionally sample a few and decide we're not going to sample some of them after all. We got limited buffering. We can have some provisional sampling. But once we throw anything out of that, it's gone forever. And so here the example is flow records. Now, of course, independent sampling of flow records is very well suited to streaming. You make a decision for each flow record as it comes, whether or not you're going to sample it. But this has statistical limitations, and principally it's the lack of control of the sample size. And so generally we're going to, as we'll see, we're going to maintain a buffer, a reservoir of these provisional selections, and in a lot of cases, if the target sample size, k, which we want to take so many records per hour, for example, this is going to be the size of the buffer we're going to work with. In terms of complexity, we need to bound the complexity, the computational complexity of processing each item. Because there may be limited computational resources at the device which does the sampling, particularly on the router, the further towards the data you get, the more expensive resources become, and the more difficult it is to tailor them to your needs. And we want no more than a weak dependence on the sample size we intend. Otherwise, it's going to limit our general utility. If we can sample 100 records per hour but not 10,000, then that's going to be a limitation. But it's probably going to be okay to have a low average cost over many items, as long as we can accommodate some processing backlog. So we may have some flexibility there. Okay, so let's turn to the statistical side. So what do I mean by sampling and estimation? So let's formalize this a little. So we're going to say that we have a population of items, I, with weights. So the set of weights W, little wi, which are non-negative. And so in the case of these flow records, they could be the number of bytes or the number of packets represented in the flows. But really, depending on your context, it could be something completely different. I mean, if you were thinking of something like the online social network application, it could be the number of friends a user had, or it could be, if it was a property of the links, it could be some joint property of the nodes at the end of the links. There, we don't necessarily have the streaming constraints, but we still have the large data set constraints. So we want to estimate the weight of subset sums. So in other words, for some subset k of all our items, we want to estimate the total weight of all items in that subset. Now, in our formulation, sampling and estimation corresponds to randomly adjusting weights. So we're going to replace each weight wi by some random adjusted weight, w prime I, which is going to be 0 if the item's not sampled. And it's going to be adjusted. The main reason is to obtain unbiased estimates. So we're going to estimate these subset sums by the corresponding sums of the adjusted weights. So that my adjusted subset sum is just this w prime, and just adding up the adjusted weights in the relevant subset k. So yes, examples of this: total bytes of all flows to a specific destination, or the mean daily number of status updates of popular OSN users. Those are each examples of specifications of this set k. So standard approach for unbiased estimation comes from Horwitz-Thompson, which was mentioned earlier in the day. That you normalize the selected data weight by dividing it by its selection probability. And we're going to be in a happy situation of knowing what our selection probabilities are. That was more of a problem earlier on in this morning's talk. And our adjusted weight is w prime, we get by dividing by the selection probability for a selected item and setting to 0 if it's not selected. And then the reason we do this is that w prime is then an unbiased estimator of w. So the question then is, how do we best choose the selection probability, p? So, well, this is, I guess, the first of our axioms, but it comes from, I'm going to give you a couple of different motivations for it. And so let's just abstractly consider a task of, suppose you have a set of n plus 1 of these weights, w1 up to wn plus 1. And our task is to eliminate, we're going to sample n of these. Correspondingly, we're going to eliminate one of the weights and leave n remaining. And The question then is, which of the selection how could I choose the selection probabilities pi to minimize the average estimation variance of a single item? So over all the n+1 items, how do I choose pi so as to minimize the estimation variance? Well, I'm going to eliminate, if my selection probabilities are pi, then my elimination probabilities, qi, are 1 minus pi, and I'm going to eliminate 1 and exactly 1 item. So the elimination probabilities sum to 1, or in other words, my selection probabilities sum to n. And that's not surprising. If I'm selecting exactly n items, I'm selecting n on average as well. And so what I'm going to do is I'm going to minimize the sum of my variance, sum over my n+1 items I of the variance of the adjusted weight, because that's my estimator. Well, this is just very simple to write out, but subject to my probability constraint. And the solution to this minimization problem is that my probability is this minimum of 1, and well, it's proportional to the weight. So where the constant here, tau, is chosen in order to fulfill this normalization constraint that my selection probabilities sum to n. So apart from this min part, I've got my inclusion probability is proportional to size. So if I look at how the probability varies with the weight, you could say it's proportional to weight, but proportional to size is the sort of traditional statistical terminology. But I have this cutoff at 1 for weights above this threshold tau. And in fact, this formulation is very simple in terms of my estimate, because remember, to get my adjusted weight, I just divide by my selection probability. If W is greater than or equal to tau, then I'm selecting it with probability 1, so my adjusted weight is just the original weight. However, if my selection probability is less than 1, then my adjusted weight turns out to be tau, the threshold. So I replace some sort of arbitrary distribution of initial weights with a set of large weights, those greater than tau, and the small weights which become equal to tau. And the only sort of random thing there is which one I'm going to choose to discard.
So you, of course, you know the sizes in advance, so you know which PIs would correspond if you know the I.
Yeah, I'm always assuming I know, like with the flow records, I know what size they are when they come in. They're completed flow records rather than, the harder problem of looking at it packet by packet. Well, let's see how IPPS, inclusion probabilities proportional to size, arise in a related context. And this is, here, suppose our aim is to keep the sample size and the estimation variance small. Well, let's express a cost as a linear combination of both these components. We can actually do this with a single item of weight x. I think I should have said weight w. Weight w and selection probability p. Then my cost is my expected number of selected items is just p, the selection probability, and my variance of my adjusted weight is what it was before, and that's going to put in this suspiciously familiarly labeled tau squared as my constant of proportionality. Well, it turns out that the cost is minimized by choosing our friend p tau w as before, this minimum of w over tau and 1. But here the interpretation is a little bit different. Here tau is, previously tau was just a function of my data and the fact I was selecting one item to discard. Here in this context I think of tau as an independent parameter. And in fact, that's actually what we do. One of the things we do in our flow measurement infrastructure is we use independent flow record selection with this inclusion probability proportional to size, where we tune the parameter tau to get a volume of flow records we can accommodate. We also call it threshold sampling, named after the threshold tau. Okay, this isn't in my view that's an old method. It's not one of the new methods I was going to talk about. So we'll come on to newer methods, although this isn't still the subject of my talk. well, suppose we want to fix the sample size. So suppose we want to select exactly k items from a population of n items, where n's larger than k. So for example, I want to select 1,000 representative flow records per hour. Or in the OSN context, suppose you want to report on a query, field a query which says, I want to know a user's friends and followers, and you're going to report them in groups of 100 so as not to overwhelm your own database system. And that's what Twitter does, in fact. So there are all sorts of they don't do it this way, but there are all sorts of contexts in which you want to sample a fixed number of records. So yeah, using the independent sampling, which you just talked about, is no good because it's stochastic. You have a variable size sample. Even the mean size depends on the population characteristics. So it's clear we need some form of dependent sampling. Independent sampling isn't going to give us the control we need. So, well, let's think about strict control of the total estimation variance. What is the variance of one of these adjusted subset sums? So remember, an adjusted subset sum is just the sum of the adjusted weights of all the flows, all the items in the index set k. So I can think of what the variance of the total is. Well, I've got the variance of the individuals plus the covariance of the cross terms. Now, of course, independent sampling was really nice because I knew I had 0 covariances. So in some sense, it became simple because I knew that the variance of this subset sum was just equal to the sum of the variances. And the sum of the variances of individual items is very easy. You have an unbiased estimate of this directly from the measurements you make. So this is very nice. You can once you've made a measurement and provided an estimate, you can automatically put error bars on that, which you can use to answer questions like, if I measure X bytes of data, what's the chance that it was really Y bytes? Higher or worse. Now there is a scheme with a fixed sample size and 0 covariances. So it's interesting. It's kind of subtle. The selection is dependent, but the covariance of the selection of different flow records is dependent. But it happens that the covariance of the adjusted weights are 0. So it's and those are the only functions of the adjusted weights which do have 0 covariance.
The covariance sum is 0, you mean?
Sorry?
The covariance sum is 0, or the covariance?
The covariance amongst individuals. So, and this is something we came up with a few years ago, and this is also used in the flow measurement infrastructure to make selections like those top n flow records or n representative flow records per hour. And you can think of it as in some sense, I won't go into the details. It's IPPS with a sort of random threshold which depends on the data, but it's not actually IPPS. It just looks like IPPS. And this has the property, of course, because we have this 0 covariance, that you see that this variance term still grows as the subset k grows. But if you think about it, you should be able to do better, because as the size of your subset increases, so the uncertainty resides in what you haven't sampled, and that uncertainty should go down. So in the end, if you estimated the whole of your data, you should have variance 0. You should be sampling everything. And of course, this doesn't, an expression like this doesn't give you that. So, and it turns out we can do better. In fact, you can show directly that just from the assumption of IPPS plus a fixed sample size, it gives you that the variance of the estimator of the total weight is 0.
It's because it's constrained to end up with a total weight that's a determined constant.
Right, but no, this is even no, you're still taking a finite number of samples. You're not sampling. You're not sampling your whole data set. You're just taking you're still taking k samples, where k is smaller than the size of your data set, but you're estimating the size. You're estimating the size of your total data set. So it's not you're sampling everything. Yeah, that would be a trivial case, but no. Well, let's see how that works. So let's say it's something which is equivalent, that IPPS plus fixed sample size implies that my estimate is actually equal to the true value. Well, we got some old friends here because you know, if I say I've got IPPS plus I'm going to take k samples, then I can derive the appropriate threshold function as a function of my set of weights and my target size. Because if I want exactly k samples, that means that my sum of my selection probabilities has got to be equal to k. And I know what my IPPS selection probabilities are. And there's a unique solution for tau for this equation. That's what I'm going to call it. And then let's have a proof. That's just a kind of setup. Now let's have a proof that IPPS plus fixed sample size gives us what we want. Well, if we look at the selected items, there are two kinds of items in our population. Those are what I call large items, which have weights greater than tau. Their selection probability is 1, so I get them all. So the only randomness is in the small items. Small items are the ones that are not large. So I got some random subset of those that I select in my sample. Then if I ask what the adjusted weight of this corresponding to this subset is, well, then of course I'm just taking my actual weights, normalizing by the selection probabilities. Well, in the small weights, I get each of those the small ones each contribute tau, as we saw before. The large ones each aren't, their weights not adjusted, they contribute wi. So this part which was random actually becomes deterministic because I got k items in total. So the contribution to this adjusted weight from the small items is just one lot of tau for each of the k minus mod L, size L, large items. And this is all deterministic, so it's not random at all. So it's fixed. So the variance is 0, and I have this. Now the conclusion from this is, of course, if I go back to my expression for the variance of my adjusted weight sum, it's still equal to the sum of the variances plus some of the covariances. So because this whole thing is 0, some of these covariances must have been negative, because the variances are positive, of course. So this is good. We like negative variance. We like these negative covariances. So in fact, we're going to formalize that and say, in the summary of the statistical properties sought, here are the three of them. We want IPPS sampling using the Horvitz-Thompson adjusted weights, the unbiased estimators. We're going to have a fixed sample size k, and we're going to stipulate that we want no positive covariances between any of the adjusted weights. So previously it was clear some of them had to be non-positive. Here we're going to say none of them are positive. And we're going to call any scheme which satisfies these properties a var-opt scheme, or var-opt k, where k is the sample size. Var-opt is contraction for variance optimal. If we have time, we'll see what we mean by variance optimality, although perhaps you can see how it arose just in the setup of IPPS, that it was the IPPS selection probabilities were derived from a minimal variance condition. And well, actually, once you've figured out what your axioms are, the rest is pretty simple. And it all follows from, as long as you can show a sort of composition law. So var-opt schemes satisfy these powerful composition relationships, which again will allow us to build up any var-opt k from a single elimination step that's simple and efficient to implement. And the composition law is, suppose I have a number of sets, I1 up to IM, disjoint sets of items, and I have a number of target sizes, K1 up to Kn, for each of these. And suppose I do var-opt sampling into size Kx on set Ix, take the union over all the x's of these sets, and then finally do another outer var-opt k, sample k items out of these using a var-opt algorithm. We haven't specified what it is yet, but using a var-opt algorithm. When it turns out that all these sort of inner steps become irrelevant, I can just as well have taken the union of my original sets and done a var-opt k on them. So this is like a composition law for sampling. Well, it turns out so what you can show is that is that all the properties, the three properties I talked about are preserved under these compositions. So here's the single item elimination I talked about, and well, I guess we kind of covered that. It's only a little bit different. So it's called var opt k plus 1. This is something that eliminates one item from a set of k plus 1 items. And here it is. I mean, I'm just really saying how it actually did it. So first of all, you find the threshold tau, which corresponds to this set of items and the size k of your target sample set. And then we eliminate exactly one item and the elimination probability is just qi is 1 minus the selection probability. So what we can do is just take the unit line and divide it up into lengths into segments of length qi, because these elimination probabilities sum to 1. And let's pick one of these at random, uniformly on the line, and that's the one we're going to eliminate. And then anything else that's surviving, we just adjust the surviving weights by replacing them with their Horvitz-Thompson formula, W divided by the probability. And then we're done, because this satisfies the three conditions. We saw earlier on this is IPPS. It takes k samples, and the covariance is non-positive, which is simple to verify. So now we can do all kinds of really nice things. First of all, we can take k items, select k items from n by successive elimination. So let's see how this works using our composition rules. So this is let bracket n be the set of set of n items, and if we apply the composition rules with that I had previously, just using one subset and k1 equals k plus 1, then this is how it. So this tells me that if I'd done a var opt k plus 1 on my n, and then reduced that by 1, it's the same as var opt k. So I can iterate this, and eventually I see that I can do my var opt k on my set of size n just by starting with n items and eliminating one item at a time until k items remain, and I'm done. And I know this is var opt because of my iterating this single step elimination is a var opt operation because of my composition rules. And we can do streaming as well. So that's another example of our rule of the composition rules. So in this case, you get that if I had done my var opt k on n minus 1 items, on the first n minus 1 items, then brought in the nth item, and then did an elimination of one of those items from that union, it would have been just the same as if I had just started with my n items and done var opt k. And if you iterate that, what you get is that equivalently you're initializing your sample set to be the first k items, and then as each successive new item I comes in, I'm going to take my current set S, which has k items, append the new item, and then do my single step elimination. And that's going to be my new sample set. And I just do this as new items come in.
Is this all, is it right to say, is this equivalent to sampling k items out of n without replacement, but implemented via elimination?
Well, I mean, I certainly think of it like that, and there are algorithms to do that, but none of the algorithms we're aware of have the computational properties which I'm going to come on to deal with. I mean, part of that is the simplicity. The nice thing is that at each step, the adjusted weights contain all the relevant information. We no longer need to know anything about our original data. And that, I think, is one of the things that has been missed in the existing literature. So I mentioned the computational properties. Well, we have two different implementations. and one is order log k per item. So, well, this arises because we can represent the large weights and the small weights separately in sorted order in a binary search tree, which has depth log k. And so when we want to locate, what we want to do is, when a new item comes in, we're making a selection. We're also transferring, for example, if a new large item comes in, some formerly large items will become small. And we need to go down through our tree of large items, deciding which ones are going to become small. So that's where the cost comes in. But all this stuff, is a depth k, and also if we want to find a new threshold, we do that by binary search on k items, and that's also log k. So altogether, it's log k. There's also another implementation using priority queues, which is log k per item, at least average over a set of I items. Okay, so here we're representing these large and small items using priority queues, and to do extraction and insertions from those, it's it's cheaper than the tree. It's only log k. But the problem is you may have to do up to k insertions for a new single item. And I can talk about the example I just gave. When you may be sitting happily with some number of small and large items, then a really large item comes in. And then I've got to start getting the smallest large items and start taking them from the large item, putting the small items next one, and so on. So making the large items become small until I've made enough of them become small. But I could have to do that for nearly k of my items. So for a single item, it could in fact be order k log k. So I might have to do k of these insertions. On the other hand, if I've done that, I don't have to do that anymore for any more large items that come in, because no other item is going to be able to do that, at least for the next k or so items. So it turns out that averaged, it's still going to be order log k averaged over my k items. So if I can, even though I might take a bit of hit on a single item, if I can at least amortize this cost over a larger set of items, then I'm okay. So if I can sort of buffer my processing demand, I'm okay. Well, I talked about the variance optimization. I just want to revisit this. And there's a general property. If you're selecting k items from a set of n items, n's larger than k, and using unbiased sampling and estimation, any scheme, an offline scheme even, let v sub m be the average of the variance of my adjusted weight sum over all subsets m of a given size little m. Now, for any scheme, this identity holds, where basically the Vn, this average, is a linear combination of two things. The sum of the adjusted single weight variances, so that's what I mean by sigma v, and the variance of the total weight estimate. Now, varopt minimizes both of these. We saw earlier that IPPS minima was chosen just to minimize sigma v, and we saw earlier that IPPS plus the fixed sample size constraint gives us that the variance of this sum is equal to 0. So we can't do any better than that, whatever we do. So there's actually no offline scheme, any scheme, has a smaller average variance in this sense than the online scheme varopt. So that's the reason we call it variance optimal. So here's an experimental illustration. We use the net flow price data set. So this comprises reviews of about 17,000 movies by a set of reviewers. And well, in our scheme, what we're going to do is we're going to assign each movie I a weight, which is the number of reviews. That should be a lowercase I. It's the number of reviews of the movie I. And we're going to sample 1,000 movies, and then you can say in a general way, for any subpopulation k, we want to estimate the total reviews. We have an estimate for the total reviews that were made of that subset. And to illustrate, the relations of variance to subpopulation size. We created subpopulation partitions of the movies of different granularity. So we partition the movies into groups based on ranges of release year. So ranges of 10 years, 5 years, 2 years, 1 year, and 0 years, which is just individual movies. So for each of these sizes of partition, we have an accuracy measure, which is basically we take. So here, K is some subset within this partition for a given number of years, and we ask what is the sum square error of the weight estimates, the sum over all the elements of the partition. And we compared 4 different sampling algorithms, VAR-opt, our former priority sampling, and 2 variants of probability proportional to size sampling without replacement. Since those seem to be the ones to, I mean, in terms of accuracy performance, those are the ones to beat. And so here's the error as a function of the query range size. So 0 individual is up here. Now we've got 1, 2, 5, and 10. And it's interesting to read off the behavior. So, you know, both priority sampling and the range conditioning version of probability proportional to size sampling without replacement have the zero covariance properties. So their error is essentially independent of the range size, because we're just whichever way we're doing it, we're just summing up those variances over all the elements. However we do the partition. For the variance optimal and the subset conditioning, they both have negative covariances. So here the error we have is going to be decreasing in R, and that's what we find. Now the two PPS methods, they both have the same individual variances, so they have the same error at R equals 0. Priority and the variance optimal, they also have the same error on individuals, but it's smaller than it was for the two PPS methods. So if you put all these things together, then it turns out that the VAR-opt is the winner in terms of variance. Okay, so I'm going to finish by summarizing. So we were motivated by accurate estimation from these sample measurement streams, and it's increasingly important for internet measurement as we're measuring flows in more and more places. We have more and more data. And we formulated these VAR-opt statistical requirements for sampling and estimation, and based on very general considerations of fixed sample size and variance minimization. And then we were able to establish these composition rules for any VAR-opt sampling scheme, which allowed us to admit this iterative formulation based on single item elimination. And furthermore, can express stream sampling into a reservoir K just as a series of these single step iterations. And VAR-opt is indeed variance optimal in the sense that it gives this minimal average variance of the adjusted weight over subsets of a given size. And then we have these efficient implementations, which what's going to really make it work in the streaming context. It's algorithmically simpler than previous approaches, and these specific dependencies are very weak in terms of the size of the number of items we want to sample. So we don't expect to encounter any size-dependent obstacles to implementation. That's my talk.
Some questions.
I have just a clarification question, just in terms of so if you knew the W's, if you know all the W's beforehand,
Yeah.
you could sum the W's and you've solved the problem, right? Because the weights. So when you say, do you observe the weights as you go along? This is a clarification question. So if you observe the W's as you draw the samples, that's...
Right, you have the samples, you know the W's for a given item when you make the sampling decision.
Only when you make the sampling decision. You don't obviously have them in advance or anything.
No.
You only observe them. And so the other question is, and it's related to the Netflix example, for each of the different sampling schemes, how many did you need to observe for each of the different sampling schemes? When I say observe, to draw the samples. Is it exactly the same for each set, or does your method actually take a look at more samples?
No, each of them work the same way in the sense we had a buffer which could accommodate 1,000 samples, and then so we took the first 1,000, and each of them as the next one came in, we had 1,001, and then we made a decision of which of those 1,001 to discard. And then when the next one came in, we made the same decision, and so forth. So
you looked at exactly the same numbers of movies.
Yes.
For each of the methods.
Yes.
You looked at, even if how many you retained.
Even if what?
So you've got how many you retained, and then how many you actually sampled to determine the weights of the W's.
Right. So I mean, in our case, it was the same. I mean, our buffer was 1,000 items, and we came up with 1,000 items. In the end, you could more generally consider these two not. You could have some final elimination step in principle, and that in some sampling schemes that can buy you some efficiency. For example, in the priority sampling scheme, you can improve on efficiency by in fact keeping 2,000 as you go along, and then making a final selection down to 1,000. So there can be some trade-offs there too.
Yeah.
And what do you do if each record has more than one weight? You want to be able to compete?
Well, yeah, that's the. I would say normally, if you're interested in doing that, it's because you have weights which mean very different things. For example, it could be unit weight for a flow compared with number of bytes.
Yeah.
And in that situation, I mean, one of the things we've looked at in the past is trying to say, can we find a combined scheme which combines the weights and allows us to do this? And the answer we found was the more disparate the weights, so the less worthwhile that trade-off is, which is in some sense not surprising. If you're trying to do two different things with a single combined weight, which are very disparate, you're not going to do very well on either. So I think if you've got weights which are distinct enough to be important, you probably want two separate samplers.
Okay, well, thanks again, Nick.
Thanks.